Alright, so we spent the last few videos talking about line integrals. Now it's time to talk about the fundamental theorem for line integrals. So we had the fundamental theorem of calculus, which went like so, back in Calc 1 or Calc 2. You have the integral from a to b of some function f with respect to x, and then that is equal to f's antiderivative evaluated between b and a. It's fairly simple. We do it all of the time now. We're going to generalize this to the idea of a line integral. So we take in a vector field as opposed to a function, continuous function on the domain. Okay, anyways, let's try this out. So the fundamental theorem for line integrals says that the integral over curve C of the gradient of some potential function with respect to the displacement vector dr is equal to that potential function evaluated at r of b minus the potential function evaluated at r of a. This should be very easy. So this implies that given the existence of a potential function, so there must be a potential function, there must be some f such that, there must exist some big F such that if I take the gradient of a potential function, I will get that vector field. That's not the case, then this theorem doesn't work. So let's try an example for this. We'll check it out. Now, find the work done in a gravitational field from 3,412 to 220. Okay, so what we need to use is the universal law of gravitation for this. So that says that the force is given by negative gmm. Those are all constants. G is the universal constant of gravitation. M is the mass of whatever you're orbiting around, and m is the mass of whatever's moving around, over r cubed magnitude times r direction. So this is like a unit vector. It tells us the direction of the field. We won't concern ourselves very much with that. You will recognize this more as the force is equal to the gmm over r squared, and that's the one that we're going to use. It's not in vector form, but it's going to be easier for us to deal with a little bit. And both of these forms are equal. One just is in scalar form, which is fine. So now what we're going to do is we are going to make a substitution. So we are going to say that the gradient of f is equal to f. So we're going to find some little f such that we get big F when we take its gradient. Now we're going to let r equal the square root of x squared plus y squared plus c squared. We're in three-dimensional space, and we can use Cartesian systems. And that's what they have here. That's what they have here, so we need to transform it into Cartesian systems. No worries. And the good thing about having this r here is that we don't need to find the potential function by taking integrals with respect to x, y, and z. We only need to take it with respect to r, because the gravitational force is something that's spherically symmetric. It only depends on your distance away, so it doesn't depend on your angle. If I have a sphere around my mass, which is at the 0 there, this is a sphere here. If I have a force at this part of the sphere, that's going to be the same as at this part of the sphere. It's independent of what angle I have, but if I have it closer, like there, then it's going to be different because the distance is different. So anyways, what we can do is we can just integrate this normally. So we get f is equal to negative gmm times the integral of dr over r squared. The integral of dr over r squared is pretty simple. You just get negative 1 over r. And then that will cancel out with our negative sign at the beginning. So we get gmm over r. So you'll recognize this as being the potential function for gravitation. If you took like AP Physics or whatever, you always know that the potential function, which I like to call the potential function big V, is equal to gmm over r, right? So now what we can do is we can plug in r for the square root of x squared plus y squared plus c squared, and now we're ready to integrate. So the integral of f dr is equal to f of 220 minus f of 3,412. And that, when we plug everything in, is gmm times 1 over 2 rad 2 minus 1 over 13. Now that's an example. Again, it's fairly easy now that we know the fundamental theorem of line integrals. Now all we need to know how to do is be really good at taking the potential functions of these vector fields, which is finding some function such that its gradient is the vector field, right? All right, so now what I'd like to do is do a brief technical aside before we jump into our next topic in the next video. That is called path independence. So path independence is exactly what it sounds like. Normally, if I have some vector field, if I take its, so say I've got a vector field and it's in two-dimensional space. Let's make that. So it'll be a little bit easier for us to understand. So here's our vector field. We've got vectors all over the place, pointing every which way. My goodness. And we're starting at point A and we're going over to point B, right? So normally if I take the integral over a path like this, so that's C1, the work done will be different than if I take the integral over a path like this, C2. They both end at the same place and they start at the same place, but because they're different paths, the work will be different. However, by the theorem that we have, the fundamental theorem of line integrals, so if I'm taking the integral over the gradient of f dot dr, well then that will be the case, that it will be the same. If I take the integral over the gradient of a function, the potential function, that will be path independent. No matter what path I take, it'll be the same. So I will do the same work no matter what path I take if I'm taking the integral over a gradient, if the fundamental theorem of line integrals applies. So this means so basically, I think we covered this a couple of videos. If there is a potential function such that the gradient of that is equal to some vector field, then I have a conservative, if I can derive a potential, if the force is derivable from a potential, then I have a conservative vector field. So immediately, if I'm taking, if I know that there is some potential function f, that I can take its gradient, then by definition, if I'm taking the line integral over a gradient, then it will be path independent. So integrals on conservative vector fields are path independent, and conservative vector fields means that you can derive it from a potential. So a way of saying this a little bit more succinctly is if I want to take the integral, or if I take the integral over f dr, this is path independent if and only if the integral over a closed loop, that's what the circle in the middle of the integral sign means. If I take the integral over a closed loop of f dr is 0. So that means if I have my vector field and I take, if I'm going from A to B, and I take an integral from here, then I go back a different way, this must be 0. And it doesn't matter which closed path I take. I could take any closed path. As long as it is a closed path, I will get, this